Welcome back. So today we'll consider a practical circuit that allows us to store bits both 0 and 1 in the same circuit and allows us to retrieve those bits when we need it. And this will be a more practical circuit, and this circuit is known as a basic SR latch. Right? This is going to be a basic unit of memory. We will be actually discussing many other units also, but all will be based on this core element. Fine. And you can construct a basic SR latch using NOR gates or using the NAND gates. Fine. But in our discussion, what I'll be discussing here in these videos, in these lectures, we will consider the basic SR latch, which is made of NOR gates. Fine. We have discussed the NOR gate. Now, for your reference, here is a NOR gate, a two input NOR gate. A, B are the inputs, and C is the output. This is its truth table, and from here I can make a generalization that if one of the inputs of a NOR gate is 1, then regardless what the other input is, output is always going to be 0. You don't need to wait for another input. If one of the inputs of a NOR gate is 1, then output is always going to be equal to 0. Okay? So I have two NOR gates here. One is in blue, the other one is in red. The blue one of the inputs, it is S, and S stands for set. And the lower NOR gate, it has one of the inputs as R, and R stands for reset. This terminology will be clear soon when we actually go through the operation of this circuit, and you'll come to know why we call S set and why we call R reset. But for your record, set in digital logic means 1, and reset means 0. Okay? If you remember last video, I told you that we had introduced a very important term as far as sequential circuits was concerned, the term of state. Right? So when I say a circuit is in the set state, I think I have it here. Okay, here it is. I said state of the sequential circuit. So whatever is stored in this memory defines the state. So if I say my circuit is in a set state, it means this memory stores 1. Similarly, if I say my circuit is in a reset state, this means this memory element stores 0. So these things will be clear as we move along. So here I have two NOR gates. One of the inputs is well defined. And now, like I said in the previous video, to construct memories, we need some sort of feedback. So what I will do is I will get a feedback connection, but in a different way. I will take this output and feed this output to the second as the second input of the lower NOR gate. Similarly, from the lower NOR gate, I'll take the output and feed this output as a second input to the upper NOR gate. Fine. And then will call this as Q bar. Bar means complement, and this output as Q. Fine. So this is a simple circuit that I have constructed using NOR gate. It has two NOR gates. The upper one has one direct input that I'm calling S standing for set, and the lower NOR gate has a direct input R standing for reset. And then I have a kind of a crisscross connection wherein the output of the upper NOR gate is fed back to the input of a lower NOR gate, and the output of a lower NOR gate is being fed back to the second input of the upper OR gate. Okay, now let's try to understand how does this circuit behave. Right? So I will start with the condition. I will start with the condition wherein I will assume, let me just copy this here. Fine. So wherein I will assume that initially both S and R have a value of 0, something like this. S is equivalent to 0 and R is equivalent to 0. Fine. Yeah, we'll do one thing because this is an OR gate based implementation. So let's start with the condition wherein S is equivalent to 0 and R is equal to 1. This will be a more appropriate condition given that the NOR gate behaves, gives an output 0 for an input of 1. Let's start with this condition. S is equivalent to 0, R is equivalent to 1. Fine. Now the upper NOR gate, it has one of the inputs as 0. So based on this input, we cannot tell what this output is going to be. Fine. But the lower NOR gate, it has one of the inputs as 1. And you know from the behavior of NOR gate that if one of the inputs is equivalent to 1, regardless of what the second input is, the output will be 0. So this NOR gate, we will show it by a dashed line because one of the inputs is 1. So based on this input, we should actually show it with a different color so that we are able to recognize it. Let me decrease the font. Okay. So based on this input, this output will go to 0. Fine. And when this output goes to 0, it is being fed back to the upper NOR gate. So what will happen after some time, this output through this feedback connection will make sure that this input also is equivalent to 0. Now both the inputs of the upper NOR gate are defined. S is already 0. Now this input is also 0. And when both the inputs of the NOR gate are 0, output will be 1. So this will trigger Q bar equivalent to 1. Okay, fine. So we normally show it using a simple timing diagram. I will draw it here. Timing diagrams are very important as far as sequential circuits are concerned. So I have a lower pulse for S and let's say a high pulse for R. Fine. So the first one is S, second one is R. Fine. And as R goes 1, first of all Q triggers, so Q will change to Q will change. There will be some delay, and based on this, somewhere here Q will change to 0, and this Q will later on, as it goes to the upper NOR gate, will trigger the output of the upper NOR gate, which means after some time Q bar will change to 1. Timing is very important here. Fine. First R goes to 1, then there is some delay, this much of delay. So first Q goes to 0 based on the behavior of the NOR gate. That Q output is being fed to the upper NOR gate, so Q bar will go 1. Fine. And later on, if we continue this process, now that this also turns, the Q bar output turns 1. So this will again be then later on fed back, which means the second input of the NOR gate will be 1. Fine. So this is what happens when S is equivalent to 0 and R is equivalent to 1. Fine. Now immediately after this, let's assume, let me see if I can copy this. I don't think it can be copied here. Anyways, we'll draw a new one. Fine. So we started with this condition. So this was my first condition, wherein S is equivalent to 0, R is equivalent to 1. So first of all, it triggered Q. So we'll actually show it like this. Q changed to 0. Then that Q was fed back to the upper NOR gate, which triggered Q bar is equivalent to 1. Right? Now, immediately after this, I will make S, I will keep as it is. Fine. And R, now I will change it to 0. Fine. Immediately after this, after we have achieved this state, immediately I will make this state. Fine. So it means something like this. Let me just quickly draw the circuits here. This is the upper NOR gate. Then I have the lower one. Then I have the feedback connection. First, I will have the direct inputs. Direct input here. Then something like this. Likewise, a direct input. Then the feedback input. Right? Now, at the end of the first condition, we have achieved something like this. This was the state. S was 0. Then this changed to, this is Q, it was 0. Then this ripple here, so Q bar changed to 1, which made sure that the second input is also equivalent to 1. Now in the second condition, I'm keeping S is equivalent to 0, but what I am changing is this. R is equivalent to 0. Fine. So I had achieved this state, this one. Now, with this as the previous state, my next state is defined like this, wherein I am keeping S is equivalent to 0, but R I am changing to 0. Fine. And now when I make this change, the lower NOR gate still has one of the inputs as 1. Fine, because of this feedback connection, which means its output will continue to stay at 0. Fine. So this will continue to stay at 0 because of this. Earlier it was because of this input. Now it is because of this input. So this is 0. It will be fed back here, which means again this input will be 0. So both the inputs are 0. So Q bar will continue to stay at 1. So this means once I have achieved this state, then even if I change R is equivalent to 0, then this state will be maintained. Q will still be equivalent to 0. Q bar will still be equivalent to 1. Fine. So as of now, what I have established is that the first state S is equivalent to 0, R is equivalent to 1, sets up Q is equivalent to 0, Q bar is equal to 1. Fine. Now, mainly in a latch, we are interested in this output. This is what is being fed to the real world. Q bar is just for explanation. Fine. But you have to make sure that Q and Q bar are complementary to each other. Fine. So Q is equivalent to 0 means this circuit right now is giving me an output of 0. That basically is the reset state. Fine. So what I have established here, as the reset out input goes to 1, my circuit, maybe I should put it something like this, when set is equivalent to 0 and reset input is high, the circuit, the, yeah, like I said, we call it an SR latch. The SR latch goes into the reset state where Q is equivalent to 0. And this is what sets up the state. There are two things: how you achieve a particular state, and second, how you maintain that state. So by putting R is equivalent to 1 in this circuit, I have attained the reset state where Q is equivalent to 0. And then later on, once I have achieved this state, Then when I put set is equivalent to 0 and reset is equivalent to 0, this reset state is maintained. Fine. So this is important. How you set up a particular state and how you maintain a particular state. Fine. So this is the same circuit. Q is equal to 0. So I'm able to store 0. I'll end this video here. Next video, we'll proceed further.